In this video, you will learn how to solve different problems on variable separable differential equations. So what is a variable separable differential equation and how to use separation of variables to solve a differential equation? So let's start with the definition of separable differential equation. So a separable differential equation is any equation that can be written in the form y prime equals f of x times g of y. And the term separable here refers to the fact that the right-hand side of this equation can be separated into a function of x times a function of y, and that all terms containing x and y must be grouped with dx and dy respectively. And if we can group them by dx and dy, that differential equation is said to be variable separable. So let's try solving some practice problems here. Let's say we're given tangent squared y dx equals secant squared dy. Now to solve this, we group all terms containing x with dx, and we group and all of the terms containing y with dy. So we can divide both sides by tangent squared y secant squared x, and then tangent squared y here cancel out, and then secant squared y as well. Then we are left with dx over secant squared x equals dy over tangent squared y. And then we integrate both sides. Now we have a problem because we cannot directly integrate 1 over secant squared x and 1 over tangent squared y. So we can use the trigonometric identities to make this integrable. Now let's take a look at 1 over secant squared x first. So 1 over secant squared x, we knew that cosine x is just equivalent to 1 over secant x. So that means if we square this one, this would give us cosine squared x equals 1 over secant squared x. Therefore 1 over secant squared x is just equivalent to cosine squared x. Now let's check if cosine squared x is integrable. Cosine squared x isn't integrable, so we need to write this again using the trigonometric identities to make this integrable. Now using the double angle trigonometric identity, cosine squared x is just equal to cosine 2x plus 1 over 2. Therefore 1 over secant squared x here is just equivalent to cosine 2x plus 1 over 2, which is integrable. So we can write the left hand of the equation, the dx over secant squared x, as the integral of cosine 2x plus 1 over 2 dx. And now let's take a look at the right hand side of the equation. So we have here dy over tangent squared y. We cannot integrate 1 over tangent squared y directly, so we need to use the trigonometric identities again to rewrite 1 over tangent squared y. We knew that tangent of y is just equivalent to sine y over cosine y. And now if we square square both sides, we'll get tangent squared y equals sine squared y over cosine squared y. Therefore, tangent squared y here is just equivalent to sine squared y over cosine squared y. But this is 1 over sine squared y over cosine squared y dy. Alright, so 1 over sine squared y over cosine squared y is just equivalent to, we just flip the denominator, which is this one, we flip that, then we'll get cosine squared y over sine squared y dy. Okay, now 1 over tangent squared y is equivalent to cosine squared y over sine squared y, but this one is still not integrable, so we need to rewrite cosine squared y and sine squared y. By Pythagorean trigonometric identity, we know that sine squared y plus cosine squared y is equal to 1. Therefore, cosine squared y is just equal to 1 minus sine squared y. So we can write cosine squared y as 1 minus sine squared y. Wait, let me delete this. Okay, so this would become the integral of cosine squared y, which is 1 minus sine squared y over sine squared y dy. Right. Now we can write this separately as integral of 1 dy over sine squared y minus integral of sine squared y over sine squared y dy. And we cancel out sine squared y here. This would become 1. So this is dy. And we know that 1 over sine y is just equivalent to cosecant y. Then when we square both sides, this would give us 1 over sine squared y equals cosecant squared y. Therefore, 1 over sine squared y here is just equivalent to cosecant squared y, and this one is integrable. So let's rewrite everything. So the right hand side of the equation can be written as the integral of cosecant squared dy minus the integral of dy, because sine squared y over sine squared y is equal to 1. And now everything is integrable. Okay, so let's start integrating the left side of the equation. So we can separate this. We can rewrite this as cosine 2x over 2 dx plus integral of dx over 2. Since 1/2 is a constant, and we can just factor that out, this would be 1/2 integral of cosine 2x dx plus 1/2 integral of dx. We can let u here equal to 2x, and then derivative of u is just derivative of 2x. That would be 2 dx. Therefore, dx is just equivalent to du over 2, and then we can rewrite this equation as 1/2 integral of cosine u du over 2 plus 1/2 integral of dx is just 1/2 times x. And now integral of cosine is just sine. Cosine u is sine u. So this would become 1/2 sine. We have another 1/2 from d over 2. So this would become 1/2 times 1/2. Integral of cosine u is sine u plus 1/2 x. Now we can substitute back the value of u, which is 2x. So this would become 1/4 sine of 2x plus 1/2 x. Therefore, the integral of cosine 2x plus 1 over 2 dx is just equivalent to 1/4 sine 2x plus 1/2 x. Now let's write that over here. Let's delete this. So this is just equivalent to 1/4 sine of 2x plus 1/2 x. Now let's work on the equation on the right, since we've already solved the equation on the left. Now we have here integral of cosine squared dy minus integral of dy. We know that integral of cosine squared y, this is cosine squared y dy, is just equivalent to negative cotangent y and minus integral of dy, which is just y. Therefore, tangent squared y dx equals secant squared x dy is just equivalent to, this one is equivalent to 1/4 sine 2x plus 1/2 x equals negative cotangent y minus y using variable separable. Oh, I forgot to write plus c. So the answer should be 1/4 sine 2x plus 1/2 x equals negative cotangent y minus y plus the constant c. Now let's solve another problem. Now let's say we're given xy cubed dx plus e to the negative x dy equals 0. So we now group all of the terms containing x with dx and all of the terms containing y with dy. Now we can write this as xy cubed dx equals negative e to the negative x dy. We just transpose e to the negative x dy to the right. And now we can group all of the terms containing x with dx and those containing y with dy. So we can divide both sides by y cubed e to the negative x. So y cubed e to the negative x. And then y cubed here cancels out, as well as e to the negative x here, and then we're left with x dx over e to the negative x equals negative dy over y cubed. Now we've already grouped all of the terms containing x and y with dx and dy respectively, and then we integrate both sides. So let's check if each of the sides is integrable. So this one is integrable, but this one you cannot integrate this directly. So in this case, we use the integration by parts. Now let's recall the integration by parts formula. which is the integral of u dv equals uv minus integral of v du. Now, how do we choose for u and for dv? So we have a common mnemonic, which is LIATE. So the mnemonic LIATE, we use this for choosing the value of u, or which one of these is u. So L stands for logarithmic functions, I inverse trigonometric functions, A for algebraic functions, T for trigonometric functions, and E for exponential functions. And in choosing for dv, we would use the opposite. So this is the order, the priority order of preference for choosing u. Okay, and for choosing dv, the order of preference would be the opposite: E, T, A, I, L. So we choose exponential functions first, then trigonometric, algebraic, inverse, then logarithmic. And one thing is, let's make sure that the value of dv that we've chosen is integrable. So in this case, we can choose, okay, we let u be equal to x, then du is equal to dx. Then we let dv equals e to the negative x, 1 over e to the negative x dx. Then we integrate both sides, then we get v equals the integral of dx over e to the negative x. Then we can write 1 over e to the negative x as e to the x. So this would become v equals the integral of e to the x dx. And let me delete this. Therefore, v is just equal to e to the x plus c, because the integral of e to the x is equal to e to the x. So now we can plug in all of the values to the integration by parts formula. So integral of u dv, this is our u dv, is just equal to uv. So our u here is x, v is e to the x, minus integral of v, which is e to the x, du is dx. Okay, let me delete this. Equals the negative of the integral of dy over y cubed. And we know that the integral of e to the x dx is just equal to e to the x. Therefore, this is just equal to x e to the x minus e to the x equals negative the integral of, we can rewrite 1 over y cubed as y to the negative 3 dy, and then we integrate that. That would be the negative of negative 3 plus 1 is negative 2, then y to the negative 2 plus c. We just copy x to times e to the x minus e to the x. Then we can simplify this as 2y to the negative 2 plus c. Or we can simply write all of this as x e to the x minus e to the x equals 2. We can write y to the negative 2. Oh, hold on, I think I made a mistake here. This is integral, not a derivative. So this is the negative integral of y to the negative 3 dy. So this would be y to the negative 3 plus 1, that is negative 2 over negative 2 plus c. So this would, we can simplify this as 1 over 2y squared plus c, because we can write y to the negative 2 as 1 over y squared, and then we already have a negative sign outside the integral, so there will be negative times negative is positive. Therefore the answer is this one, x times e to the x minus e to the x equals 1 over 2y squared plus c. Let's solve another problem here. So let's say we're given y prime equals cosine squared x times cosine y. Y prime is just dy over dx equals cosine squared x times cosine y. And now we need to group all of the terms that contain x with dx and y with dy. So we divide both sides by cosine y, then we'll have dy over cosine y on the left, and then cosine squared x, we multiply this one by dx on the right side. So this is now our variable separable equation. Now we integrate both sides of the equation. So that will be the integral of dy over cosine y equals the integral of cosine squared x dx. 1 over cosine y is not integrable, so we need to write this into its trigonometric identity. So 1 over cosine y is just equivalent to secant y, and this would become secant y integral of secant y dy. And for cosine squared x, we can write this by using the double angle trigonometric identity, and cosine squared x is just equivalent to cosine 2x plus 1 over 2. So we can write this, we can write cosine squared x as cosine 2x plus 1 over 2 dx. And now let's integrate both sides of the equation. Now let's work on the left side first, the integral of secant y dy. So we cannot integrate secant y dy directly. So there's a technique. We can multiply secant y by secant y plus tangent y over secant y plus tangent y dy. Anyway, secant y plus tangent y over secant y plus tangent y is just equivalent to 1, so it doesn't affect the original equation. And actually you can also solve this using partial fractions. You just don't change 1 over cosine y into secant y. You just multiply both the numerator and denominator by cosine y, and then you'll get the same answer. Alright, now let's simplify this. We distribute secant y here, so this would become secant squared y plus secant secant y tangent y over secant y plus tangent y dy. Alright, so we can use substitution here. We let u equals secant y plus tangent y, and du is equal to the derivative of secant y plus tangent y, and derivative of secant y is secant y tangent y plus derivative of tangent y is secant squared y, then dy. Now we can plug in u and du to this equation. So this would become the integral of du over u. So the integral of d over u, or 1 over u du, is just equivalent to ln of u plus the constant. And now we need to plug in back the value of u. So let's do that. Therefore, integral of secant y dy is just equivalent to ln of our u is secant y plus tangent y. And then we copy the equation or expression on the right side, which is the integral of cosine 2x plus 1 over 2 dx. Let's delete this one. Now we're done with the equation on the left. We've already solved it, and that is equal to the ln of secant y plus tangent y. And now let's work on the expression or equation on the right side. So we can rewrite this as the integral of cosine 2x over 2, so we can split that, dx plus the integral of dx over 2. Alright, since 1/2 is a constant, so we can just factor that out. So this would become 1/2 the integral of cosine 2x dx plus 1/2 the integral of dx. Then we can let u here be equal to 2x, and then du is just equal to 2 dx. Therefore, dx is just equivalent to du over 2. So we plug in that to the equation. This is equal to 1/2 integral of cosine u du over 2 plus 1/2 integral of dx is just equal to x. So this is just 1/2 x plus c. So let me delete this. Then we simplify this further. So this is equal to 1/2 integral of cosine is just equivalent to sine. So this is, we also have 1/2 here. So there will be 1/2 times 1/2 integral of cosine u du is equivalent to sine u plus 1/2 x plus the constant c. So this is just equal to 1/4 sine u. We plug in back to the equation the value of u, which is 2x plus 1/2 x plus c. Therefore, integral of cosine squared x dx is just equivalent to, let me delete this, 1/4 sine 2x plus 1/2 x plus c. So this is our final answer for y prime equals cosine squared x times cosine y. And by the way, all of the results here of the calculations, so we call them general solutions because the arbitrary constants are not yet defined. When you're given the values for x and y, then you plug in those values to the general solution, and then now we call it the particular solution. Therefore, the arbitrary constants are already defined.